Good morning, everyone. I'm Cham with matrix number 205677. In this video, I will discuss on several topics, and the first topic is the basic concepts in statics. The second topic is support system. The third topic is equilibrium in particle and rigid body. And the last one is the analysis of friction in bodies and structures under static conditions. So for the first topic, basic concepts of statics, I will touch on the mechanics, the fundamental concept, the units of measurement, and the international system of units. And the last one is the numerical calculation. Okay, now let's start with mechanics. Mechanics is a branch of the physical sciences that is concerned with the state of rest or motion of bodies that are subjected to the action of forces. Mechanics can be divided into two categories, which is rigid body mechanics and the deformable body mechanics. Under rigid body mechanics, there are statics and dynamics. Static is study of rigid body at rest, while dynamics is the study of rigid body in motion. So under deformable body mechanics, we will have mechanics of materials, which is about the strength of material, and we'll also have the fluid mechanics. Okay, so in conclusion, actual statics is the branch of mechanics which deals with the equilibrium of bodies, whether the bodies are at rest or move with a constant velocity. So now next, let's jump to the fundamental concept. So the first one is length, which is to define the distances and the geometric properties of a body. And then we will have time, which is a succession of an event. And then the mass, we can say it as the quantity of matter in a body, or we also can say it like quantitative measure of the resistance of a body to a change in velocity. And the next one is the force, which is the effect which tends to cause a body to change its state of rest or uniform motion. And we have a few examples of forces like gravitational and electrical forces and also magnetic forces. And the next one is the particle. A particle has a mass, but the size is negated. And the geometry of the body will not be involved in the analysis of the problem because particle has a very, very small size. And the next one is the rigid body, which we can say it as a combination of a large number of particles in which all the particles remain at a fixed distance from one another. And then the last one is the concentrated force, which is represent the as effect of a loading, which is assumed to act at a point on a body. And when we talk about friction, actually is related to the Newton's law. And there are three Newton's laws that maybe we have learned before in secondary school or in college. And the first law is the particle originally at rest or moving in a straight line with constant velocity tends to remain in this state provided the particle is not subjected to an unbalanced force. Okay, so it's said to be in equilibrium lah. And then we'll have the second law. The second law states that a particle acted upon by an unbalanced force F experiences an acceleration A that has the same direction as the force and a magnitude that is directly proportional to the force. So if F is applied to a particle of mass m, and this law may be expressed mathematically as F equals to ma. So you can refer to the picture down here, where there is an accelerated motion when there is an unbalanced force applied on the object. So the last one is the Newton's third law, which states that the mutual forces of action and reaction between two particles are equal, opposite, and collinear. You can refer to the picture down here. The next one is the Newton's law of gravitational attraction, which I think we are familiar with, and the formula is that F equals to G times by m1 and m2 divided by r squared. F is the force of gravitation between the two particles, and the G is the universal constant of gravitation, which is 66.73 to the power of 10 negative 12 meter cube over kg s squared. M1, M2 is the mass of each of the two particles, and the R is the distance between the two particles. So next we will have the units of measurement, which we can also call it like SI unit, International System of Units. So for temperature we'll use Kelvin, distance we'll use meter, electric current is ampere, time is second, amount of substance we use mole, mass is kilogram, and the intensity of light we use candela. So the next one is the International System of Units lah. I think we are very familiar with. We have tera, giga, mega, kilo, density, centi, milli, micro, nano, pico. So we will have the multiplication factor to represent the prefix. Actually, is our work in writing our answer instead of writing so many zeros, and we just replace it with multiplication factor. The last topic of the basic concept is static is the numerical calculation, and under numerical calculation the first one we have dimensional homogeneity, which means that the terms of any equations in describing a physical process must be dimensionally homogeneous, and this means that each term must be expressed in the same units. Okay, let's say S equal to Vt plus 1 over 2at squared. S in meter, T in second, V is meter over second, and the acceleration is meter over second square. So no matter how the equation is evaluated, the dimensional homogeneity remains the same. Okay, the next one we will have the significant figure, which is to determine the accuracy of the number. In significant figure, actually engineering notation is used. The numbers need to be rounded off to the appropriate number of significant digits and expressed in multiples, like what I stated in the last slide, right? The prefix and the multiplication factor. So for numbers that less than 1, the zeros are not significant. Example like 0.00831. So there are only 3 significant figures in that particular number, which is at 31. Okay, the next one is the rounding of numbers. If the number is greater than 5, it's rounded up, and if the is below 5, it's not rounded up. Okay, for the calculation, we don't round off calculation until we get the final result, and the answers are normally round off to 3 significant figures. Alright, I think that's all for the basic concepts in statics. So now we will move to the force system. The force system is a collection of forces acting at specific locations. So under the force system, we can categorize to coplanar and non-coplanar. Under coplanar, we have collinear, parallel, concurrent, and non-concurrent. And non-planar will have parallel, concurrent, and non-concurrent. So let's see at the collinear picture here. So where the lines of action of all the forces of a system act along the same line, this force system is called collinear force system, which is under coplanar. And then the picture below is the example of the parallel force, how it looks like. So now is the coplanar and concurrent forces. Coplanar forces is the forces acting on only one plane. You can refer to the picture up there. You can see all the forces is only acting on one plane. And then the concurrent forces is the forces when external pass through a single point, and the point is called the point of concurrency. The lines of action of all forces meet at the point of concurrency, and concurrent forces may or may not be coplanar. So this is the point of concurrency if you refer to the picture up here. Okay, this is the point. This is a point. Okay, now I would like to talk about the coplanar and concurrent force system. It's a force system in which all the forces lie in a single plane and meet at one point. And for example, forces acting at a joint of a rope truss. So you can refer to the figure down here, where you can see the point of concurrency here, and all the forces are acting on one point. So we have a P here, which is the external force, and F1 to F5 is the member forces or internal member forces. RA and RB is equal to the reaction, and C is the point of concurrency. So the next one is the coplanar and non-concurrent force system. And these forces, they do not meet on a common point, however, they lie in a single plane. For example, the forces acting on a beam. So you can refer to the picture down here. They are all react on a single plane, which is the line, but they are not on one point. It's not like a point of concurrency. It's just on a single line. So this is the difference from the force system previous. Okay, the next one is the non-coplanar and concurrent force system. In this system, the forces lie in a different planes but pass through a single point. So the example is the forces acting at the top end of an electrical pole. So when you refer to the picture down here, you can see the forces all they come from one point at the top of the pole here, and then they go to the different of the direction. So it's on different planes. So next topic, we will talk about the forces vector and the vector addition of forces. So in the addition of forces, we just want to find a resultant force. So you can refer to the picture down here. We have F1 and F2, and then we have to find the FR which uh, falls between F1 and F2 is we call the resultant force. And then we can simply arrange it to a right triangle, and then we can solve it through triangle rules later that we will discuss later. And same with the example down here. It's also where we have U and V, and then we will arrange it to a triangle so that we can do the calculation later. So now I'd like to talk about the ways to solve the addition of two forces. The first one is the parallelogram law, where we have two component forces, which is F1 and F2. You can refer to the figure A here and add according to the parallelogram law, yielding a resultant force Fr that forms the diagonal of the parallelogram. Then the Fr is lies between the F1 and F2. And if a force F is to be resolved into components along two axes, which is UV, you can refer to the figure B here. Then you start at the head of force F and construct lines parallel to the axis, thereby forming the parallelogram here. That means you can see the lines is parallel to the U and the line parallel to B. And then we will construct a line between the square here, which is the resultant force that we're going to find. And we will label all the known and unknown force magnitudes and angles on the sketch and identify the two unknowns as the magnitude and direction of the resultant force. Okay, the second way to solve the addition of vector forces is the trigonometry, which we will redraw a half portion of the parallelogram that we talked the last slide just now to illustrate the triangular head to tail addition of the components. It's just like we have two forces F1 and F2, and we just arrange it into a triangle like this. And then from this triangle, the magnitude of the resultant force can be determined using the law of cosine, which is C equals to square root of A2 plus B squared minus 2AB cos C. And its direction is determined from the law of sine. The magnitude of two force components are determined from the law of sine too. So the sine law is A over sin A equals to B over sin B equals to C over sin C. Okay, right now let's have a simple example here. So you can refer to the figure. We have the screw eye, and it's subjected to two forces. The F1 is 100 Newton and the F2 is 150 Newton. So the first step, we're gonna construct a parallelogram where we move out all the forces, and then we construct parallel lines to then we will find out the force resultant force line is force between F1 and F2. So we have to label the parallelogram with the data that we have got. Example is 15 degree here, the 10 degree here. And the next step, we have to construct a triangle, which is we are gonna use trigonometry to solve this question. And we'll have a triangle like this. And then we will use cosine rules to solve the question. So we'll find out after substituting all the data that we have, and we got 230 Newton. And then we'll use the sine rule to find the magnitude of the degree. So after insert all the data, we got 39.8 degrees Celsius. However, we want to find the direction. So Thus, the direction is 39.8 degree that we have, and we have to plus with 15 degree here to find the total direction is 54.8 degree. Okay, the next one is addition of coplanar forces system. Actually, we have three notation to about this addition. The first one is the scalar notation, where we will have the rectangular components of force F shown in the figure here are found using the parallelogram law, so that F equals to Fx plus Fy. So Fx here, Ff is y. So we will use this formula to find the F here, force. So they can determine from Fx is equal to F cos theta, and then Fy we can find from F sin theta. Okay, we can also use the triangle rule here, the SOHCAHTOA, to find the magnitude of each line here. Okay, the next one we will have the Cartesian vector notation. We are possible to represent the x and y components of force in terms of Cartesian unit vectors I and j, and they are co-unit vector because they have a dimensionless magnitude of 1, and so they can be used to designate the direction of the x, y axis respectively. You can refer to the figure here. So since the magnitude of each component of f is always a positive quantity, which is represented by the positive scalars fx and fy, then we can express f as a Cartesian vector. So when we write out the formula is like f equals to fxi and fyj. The next one is the coplanar force resultant. So the difference for this coplanar force resultant than the notation previously is they have several coplanar forces and they all lie in the same plane. So to do this, its force is first resolved into its x and y components, and then the respective components are added using scalar algebra since they are collinear. The resultant force is then formed by adding the resultant components using the parallelogram law. So you can see on the figure here, like they are different direction, and then we have to construct parallelogram for each of the force, and then we have to find the fx and fy of each of the force, and then we have to add it together. Then we'll get the formula like this. The vector resultant force is Fr equals to F1 plus F2 F plus F3, and for each of the F1, F2, F3 we will have F1x, F1y, F1 and F2x, F2y, F2, F3x, F3y. So it's quite complicated compared to the notation that we have discussed earlier. So, but anyway, we have a simplified step. So first one, we have to find the force resultant for x equals to the total of fx, and the force resultant of y is equal to the total of fy. And then the formula to find the force resultant is square root of force resultant square x plus force resultant square y. So to find the magnitude of the data, we will use the tangent Fy over Fx to find the magnitude of the degree. So you can refer to the picture here. Okay, the next topic is the Cartesian vectors, which we will have the right-handed coordinate system, the first one. So you can try on your own to identify, like the one, our thumbs always pointing up, right? This is the z-axis, and then here is the x-axis, and this is the y-axis. Okay, the second one is the rectangular components of a vector, where A is directed within an octant of the x, y, z frame by two successive application of the parallelogram law. So you can refer to the picture here. You can see the A, and you can see the z-axis, y-axis, and x-axis, and all the A's form a parallelogram through this axis. So we'll have the formula like A equals to ax plus xy plus az. So the last one is the Cartesian unit vectors. Cartesian unit vectors is the IJK that we mentioned earlier. Is used to designate the direction of the x, y, z axis. Yeah. So for the addition of Cartesian vectors, we will have one formula which the resultant force is equal to the total of force, and equal to the total of fxi plus total of fyj and plus total of fjk. The next one is the position vector. It's the fixed vector which locates a point in the space relative to another point. You can refer to the picture here, and we have the formula which is r equal to xi plus yj plus jk x, which is actually the same as the way we have discussed earlier. Just the difference is the pictures that show to you. Okay, the last topic of the force system is the force vector directed along a line. So you can see the force F is directed along the chord AB here. Yeah, it's along a line. And F as a Cartesian vector by realizing that it has the same direction and sense as the position vector R directed from A to B on the chord. So you can see the force they have the same direction as U from A to B. So we will have one formula like formula is equal to Fu, force is equal to Fu equal to Fr over R, and the formula here. So we will have to find the distance, the Xc minus Xa, Yb minus Ya, Zb minus Za, and we'll use this formula to find the magnitude of our resultant force. Okay, we will now go to the next topic, which is equilibrium. The first part is the equilibrium of a particle. So an object is said to achieve equilibrium when it remains at rest or originally at rest, or it remains at constant velocity if originally at a motion. And it satisfies the Newton's first law of motion, which requires the resultant force acting on a particle to be equal to 0. So the total F is equal to 0. Okay. For when we say about equilibrium, we will talk about the free body diagram. The free body diagram is actually a drawing that shows the particles with all the forces acting on it. And we have three types of support. The first one is the springs. We have the formula F equal to Ks, where we know that K is the spring constant that represents the stiffness or the elasticity of the spring. And then if S is positive value, that means it's elongation. If S is negative value, it means shortening. The spring is being pushed up. Okay. The next type is the cables and pulleys. A cable can support only a tension or pulling force, and this force always acts in the direction of the cable. So it just follows the direction of the cable and is always pulling force. The cable is subjected to a constant tension T throughout its length. So you can refer to the picture here. And then the last one is the smooth contact. If an object rests on a smooth contact, then the surface will exert a force on the subject that is normal to the surface at the point of contact. So you can refer to the picture here. So now you will learn how to draw a free body diagram. The first step is draw outline shape. So we will have to imagine the particle is isolated and cut free from its surroundings, and this requires to remove all the supports and drawing the particle's outline shape. And second, we have to show all the forces. The forces acting on the particle can only be active forces which tend to set the particle in motion, or they can be reactive forces also, which are the result of the constraint or supports that tend to prevent the motion. And the third step is to identify each force. The forces that are known should be labeled with their proper magnitudes and directions. Data are used to represent the magnitudes and direction of forces that are unknown. So let's have a quick simple example here. You can refer to the plate here. It's subjected to two straps A and B, and then we just cut it off from the surroundings, and we'll have like two straps here, which is TA and TB, represent the tension, and then we will have a gravitational force down here, which is 9.81 Newton. So again, in equilibrium of particle, we will see coplanar force system. So if a particle is subjected to a system of coplanar forces that lie in the xy plane, then each force can be resolved into its I and J components. So these forces must sum to produce a zero resultant force to achieve its equilibrium. The formula is like total of Fx equal to 0, total of Fy equal to 0. So total F will also be equal to 0. So you can refer to the picture down here. Okay, now let's have a very simple example. So determine the tension in cables BA and BC necessary to support the 60 kg cylinder in the figure. Okay, is the figure here. So the next step that we will have to, first step is to draw the free body diagram. So according to the question, we will draw a body diagram like this. We will have tension A, tension C, tension and B down here, tension BD. Okay, the 60 here is the weight and we will times with the gravitational force. So the weight of the cylinder causes the tension in cable BD to be TBD is 60 times 9.81. So the forces in cables BA and BC can be determined by investigating the equilibrium of ring B. And the magnitude of TA and TC are not unknown, but their directions are known. So the second step is the equation of equilibrium by applying all the equilibrium equation of x and y axis. So we have the formula here, fx equal to 0, total of fy equal to 0. So we will have two equations. For fx is tc cos 45 minus 4 over 5 ta equal to 0. And for fy, we will have tc sin 45 plus 3 over 5 ta minus 60 times to 9 at 9.81. So from these two equations, we'll do simultaneous equation, and then we solve it. Tc is 476 Newton, and Ta will get 420 Newton. Okay, now we have 3D force system. Actually, it's just same as coplanar, but it's in three dimensions. So we will resolve the forces into their respective ijk components again, and then we'll have the formula like total of fxi plus total of fyj plus total of fjk equal to 0. So we have to make sure like total of fx, total of fy, total of xj equals to 0 to achieve the equilibrium. Okay, let's have an example from the 3D force system. So we will determine the force in each cable used to support the 40 LV plate shown in the figure. So to solve this question, again, the first step we have to construct the free body diagram according to the figure given. So it looks like this. The second step, that is the equation of equilibrium. We have to express the forces in Cartesian form, and the coordinates of points B and C are given. So B is negative 3 feet, negative 4 feet, and 8 feet, and C is negative 3 feet, 4 feet, and 8 feet. So we have to insert the data into the formula, and then we have to equilibrium requires total forces equal to 0. So from the formula that generated here, we have to compare it, equating the respective ijk components to 0 years. So when we compare all these to the respective components, then we can find the answer. So FB and FB equal to FC equals to 23.6 lb, and FC is 15. Okay, now we have reached the second part of the equilibrium, which is equilibrium of a rigid body. So rigid bodies are those bodies in which the distance between particles is constant despite any kind of external force. Okay, the condition for rigid body equilibrium, the first one is resultant force and couple moment are both equal to 0. Resultant force equal to total force equal to 0. The sum of the forces acting on the body is equal to 0. So the formula is MR O equals to total of MO equal to 0. The sum of the moments of all the forces in the system about point O added to all the couple moments is equal to 0. So the formula is the total of MA equal to R times FR plus MRO equal to 0. So we have two assumptions for rigid body equilibrium, where the body will remain rigid and the body will not deform under the applied load without introducing any significant error. Okay, again we have to construct free body diagrams for rigid body. So there are two rules. If a support prevents the translation of a body in a given direction, then a force is developed on the body in that direction. If rotation is prevented, a couple moment is exerted on the body. So we have three types here. The first type is the aurora or cylinder. This supports only prevent the beam from translating in the vertical direction. So the aurora will only exert a force on the beam in this direction, is up. So the second is the beam supported by a pin, where the pin passes through a hole in the beam and two leaves which are fixed to the ground, and this can prevent translation of the beam in any direction. The pin must exert a force on the beam in the opposite direction, and we will represent the resultant force by its two rectangular components F, X, and Y. So we'll have the force exerted is here, but we have to separate it to Fx and Fy to find the total F. So the third type is the fixed support. This support will prevent both translation and rotation of the beam, and a force and couple moment must be developed on the beam at its point of connection. So now these are the supports for rigid bodies subjected to 2D force system. And the first one will have cable, and we will only have one unknown. The reaction is a tension force reacts away from the member in the direction of the cable. So you can refer to a picture. Here is the example of the first type of support, and then we will have the weightless link for the second support, and then we will have one unknown. The reaction is a force which acts along the axis of the link. And then third one is a roller. A roller, we also have one unknown only. The reaction is a force which acts perpendicular to the surface at the point of the contact. You see 90 degrees Celsius here. So the fourth one is a rocker. We also one unknown. The reaction is a force which acts perpendicular to the surface of the point of contact. So I have 90 degrees here. And then we'll have a smooth contacting surface is only one unknown. The reaction is force which acts perpendicular to the surface at the point of the contact. So you can, this is an example for the number 4 type of support, and this is the example for number 5 support. Okay, here are the other examples of the supports for rigid body to 2 dimensions. The number 6 is the roller or pin in a confined smooth slot with one unknown. The 7 is the member pin connected to collar on smooth rod, also one unknown. And number 8 will have smooth spin or hinge with 2 unknowns. The reaction are 2 components of force, or the magnitude and direction of the resultant force. So we will note that the direction and the degree are not necessarily equal, usually not equal, unless the rod shown is a link as in the number 2. So you can refer to the example here for number 8. And number 9 is the member fixed connected to collar on smooth rod with 2 unknowns. And the last one is a fixed support with 3 unknowns. The reaction are the couple moments and the 2 force components, or the couple moment at the magnitude and direction of the resultant force. This is the example for number 10. Okay, now let's have an example. So draw the free body diagram of the uniform beam shown in the figure below. The beam has a mass of 100 kg. So we will have to construct a free body diagram for this picture. Okay, this is the free body diagram that we have constructed for the figure just now. So since the support at A is fixed, so the wall exerts 3 reactions on the beam denoted AX, AY, and MA. So it's like this. AX, AY, and MA is here. So the magnitudes of 3 reactions are unknown and their sense has been assumed. And the weight of the beam W is equal to 100. We will have to time with the gravitational force, which is 9.81 Newton, and we'll get 981 Newton. X through the beam's center of gravity G, which is 3 meters from A since the beam is uniform. So this is the free body diagram that we constructed according to the figure. Next, we're gonna discuss on the equation of equilibrium for rigid body. So again, we will have total of fx equal to 0, total of fy equal to 0, and total of mo equal to 0 is equivalent to the system. Fx and fy represent respectively the algebraic sums of the x and y components of all the forces acting on the body, and mo represents the algebraic sum of the couple moments and the moments of all the force components about the z-axis, which is perpendicular to the xy plane and passes through the arbitrary point O. And we will have alternative sets of equilibrium equations. Is total fx equal to 0, total ma equal to 0, and total mb equal to 0. So you can see the free body diagram here, and when you look at the picture, so all the forces on the free body diagram may be replaced by an equilibrium force, and the total of Fr is equal to total force acting at point A. The resultant couple component is total of Mr equal to total M, and Fr must be parallel to y-axis, so that total of Fx equal to 0. Total of MB equal to 0 where B does not lie on the line of action of Fr, then Fr equal to 0 too. So now let's have an example for the equilibrium of rigid body. So the cord shown in figure supports a force of 100 lb and wrapped over the frictional pull V. So determine the tension in the cord at C here, and the horizontal vertical components of reaction at pin A. Okay. So again, we have to start with free body diagram. This is a free body diagram that we can construct according to the picture. And that is equation of equilibrium. So equation of equilibrium, we will sum all the moments about point A to eliminate AX and AY, and we'll have a total of MA equal to 0. So we insert the data, and we can get tension equal to 100 lb. Using this result, total Fx equal to 0, and we can find Ax equal to 50, and then total Fy equal to 0, we can find Ay is equal to the 187. That's all. Next, we have to discuss about 2 and 3 force members in rigid bodies. A 2 force member has forces applied at only 2 points on the member. You can refer to the picture here. So to satisfy force equilibrium, Fa and Fb must be equal in magnitude. Fa equals to Fb equals to F, but opposite in direction. So F equals to 0. Therefore, for any 2 force member to be in equilibrium, the 2 forces acting on the member must have the same magnitude, act in opposite direction, and have the same line of action directed along the line joining 2 points where these faces act. So if this example, and a simple example here is the hydraulic cylinder, which we have AD here, is a typical example of the 2 force member, since its pin connected at its end and provided its weight is neglected. Only the pin forces act on this member. So next is the 3 force members. It is a member which is subjected to only 3 forces. The moment equilibrium can be satisfied only if the 3 forces from a concurrent or parallel force system. So if the lines of action F1 and F2 intersect at point O here, picture A, then the line of action of F3 must also pass through point O so that the forces satisfy MO equal to 0. So we have the force F3 here. Okay. As a special case, if the 3 forces are all parallel, like in figure B, the location of the point of intersection O will approach infinity. So you can see from the picture here. So now we have the types of supports for equilibrium for rigid body in 3 dimensions. The first one we have table with 1 unknown. The second one we have the smooth surface support with 1 unknown also. The roller have 1 unknown. The ball and socket have 3 unknowns. The reaction are 3 rectangular force components. And the number 5 is the single journal beading with 4 unknowns. The reaction are 2 force and 2 couple moment components which act perpendicular to the shaft. So we can refer to the free body diagram. And then we have number 6 is the single journal bearing with square shaft with 5 unknowns. The reaction are 2 force and 3 couple moments components. Okay, this is the free body diagram. The number 7 is the single thread bearing with 5 unknowns also. The reaction are 3 force and 2 couple moments components. And number 8 is the single smooth pin with 5 unknowns. The reaction are 3 force and 2 couple moment components. Number 9 is the single hinge with 5 unknowns, and we have 3 force and 2 couple moment components. The last one is the fixed support. We have 6 unknowns. So we have 3 force and 3 couple moment components. As a summary, we have to study the equations of equilibrium for rigid body. The first one is the vector equation of equilibrium, which you have total of F equal to 0, total of MO equal to 0, where the total F is the vector sum of all the external forces acting on the body, and the total MO is the sum of the couple moments and the moments of all the forces about any point O located either on or off the body. The second one is the scalar equations of equilibrium. So we will have the formulas here. So if all the external forces and couple moments are expressed in Cartesian vector form and substituted into equation phi over phi here, the equation here, so we'll have the formula like this. And since the ijk components are independent from each other, so the above equation are satisfied provided. So we will have like a 6 scalar equilibrium equation here. We can solve up to at most 6 unknowns. Like we have 10 types of supports that we studied on the previous slide. Right, we can use this equilibrium to solve the questions up to 6 unknowns. And equation 5.6a for this, it requires the sum of the external force components acting in the x, y, and z direction to be 0. And for equation 5 to 6b, it requires the sum of the moment components about the x, y, and z axis to be 0. So finally, we have reached the last topic, this analysis of friction in bodies and structures under static conditions. Friction can be defined as the force resisting the relative motion of fluid layers, solid surfaces, and material elements gliding against each other. So what is static friction? It's a force that keeps an object at rest. So the friction experience can be also defined as the friction experience when individuals try to move a stationary object on a surface without actually triggering any relative motion between the body and the surface which it is on. So example in our real life lah. The first one is a papers on a tabletop. The second one is a towel hanging on a rack. And 3 is a bookmark in a book, and also a car park on a hill. It's all about static friction that can make this object remain at rest. So we have 2 laws for static friction. The first one is the maximum force of static friction is not dependent on the area of contact. And the second one is the maximum force of static friction is comparative to the normal force. And if the normal force increases, the maximum external force that the object can endure without moving also increases. This is the picture that represents the static friction. And we will have coefficient of static friction, which is the coefficient of static friction equal to static frictional force over normal force. So now we have to learn about dry friction, or we call it a column friction. It occurs between the contacting surface of bodies where there is no lubricating fluid. So the characteristic of the dry friction, the first one is the frictional force acts tangent to the contacting surfaces in direction opposed to the motion of tendency for motion of one surface relative to another. The second characteristic is the maximum static frictional force that can be developed is independent of the area of contact, and provided the normal pressure is not very low nor great enough to severely deform or crush the contacting surfaces of the body. The third characteristic is the maximum static frictional force is generally greater than the kinetic frictional force. for any two faces of contact. And the number 4 is when slipping at the surface of contact is about to occur, the maximum static frictional force is proportional to the normal force. So the last one is when slipping at the surface of contact is occurring, the kinetic frictional force is proportional to the normal force, such as kinetic force is equal to the coefficient of static force times with the K and Newton. Next, we have to discuss on problems involving dry friction, and we can divide into three types. The first one is the no apparent impelling motion. It requires the number of unknowns to be equal to the number of variable equilibrium equations. It must satisfy the inequality F is smaller than mu Fn, otherwise slipping will occur and the body will not remain equilibrium. Okay. So the next one is the impelling motion at all points of contact. The total number of unknowns will equal to the total number of available equilibrium equations plus the total number of available frictional equations F equal to mu Fn. So when motion is impending at the points of contact, then Fs equal to mu Sn, whereas if the body is slipping, then Fk equal to mu Kn. The third one is the impending motion at some points of contact. The number of unknowns will be less than the number of available equilibrium equations plus the number of available frictional equations or conditional equations for tipping. So now let's have a question with a solution. So the uniform crate shown in figure has a mass of 20 kg. If a force P equals to 80 Newton is applied to the crate, determine if it remains in equilibrium. The coefficient of static friction is mu equals to 0.3. So from the figure here, we have to construct a free body diagram. So as shown in the figure, the resultant normal force NC must act a distance x from the crate's center line in order to counteract the tipping effect caused by P. So there are three unknowns, which is F, NC, and X, which can be determined strictly from the three equations of equilibrium. So we have already constructed a free diagram here. And then from the equations of equilibrium, Fx equal to 0, total of Fy equal to 0, so we will get two equations. For Fx is Ft cos 30 degree Newton minus F equal to 0, and negative 80 sine 30 degree N plus NC minus 196.2 Newton equal to 0. So we will do the simultaneous equation, and then we will get the answer F equals to 69.3 Newton, NC equal to 236.2 Newton, and the X we get is negative 9.08 millimeter. So since X is a negative value, like it indicates the resultant normal force slightly to the left of the crate center's line, no tipping will occur since X is lower than 0.4 meter. Also, the maximum frictional force which can be developed at the surface of contact is you can find from mu times NC, and is equals to 70.9 Newton. Since F is 69.3 Newton and is smaller than 70.9 Newton, so the crate will not slip, although it's very close to doing so. So that's all from me. Thank you for listening.